Hi everyone, I welcome you all to the another video lecture session on the subject of strength of materials. This will be basically on the topic of thin cylinders. Before going further, let me introduce myself. I am an alumni from IIT Varanasi who is presently working in the GATE Academy Private Limited. So in this lecture, I would like to explain you how to find out stresses induced inside the material of a thin cylinder. Before going further, I would like to show you the classification of pressure vessels. Basically, pressure vessels are classified into two categories based upon a ratio, which is radius to thickness ratio. So, if the radius to thickness ratio is greater than 16, we will take it as thin cylinder or thin pressure vessels basically, and the ratio is less than 16, we will take it as a thick cylinder or a thick pressure vessel. So, if a cylinder is like this, so this is its radius here and the thickness is given by T. So actually the material is only along this thickness. So if this radius to thickness ratio is greater than 16, we will take that as a thin pressure vessel or a thin cylinder. So if it is not, or if it is less than 16, we will take it as a thick pressure vessel or a thick cylinder. So basically pressure vessels are classified into two categories, spherical pressure vessels and cylindrical pressure vessels, but our GATE syllabus is concerned with respect to only cylindrical pressure vessels. So whatever we're going to study, that will be corresponding to only thin cylindrical pressure vessels. Now let me explain you the assumptions we're going to take for this concept of the thin cylinder. So if you see the assumptions, the first assumption is that the weight of the container is neglected. So strength of material subject is an ideal subject. So until and unless it is asked in the question to consider the weight of the component, we never consider the weight of the component there. So weight if the container is neglected. Second one is we're going to deal with the cases where only internal pressure is acting. So we don't deal with the stresses induced inside the thin cylinders if some external pressure is acting there. And the third and fourth assumptions are circumferential stress is uniform over thickness and radial stress is neglected for analysis. So, you will understand regarding the circumferential stress and radial stress very thoroughly once I explain you the types of stresses induced inside the material of a thin cylinder. So, stresses in thin cylinder. If you take a three-dimensional view of a thin cylinder, it would be looking like this. So, if you take the front view, it will be like this. And side view will be like this. So this one is experiencing some internal pressure, maybe because of a fluid which is of a gas type or a liquid type. So the intensity of the pressure is shown using these arrow marks here. So if you see the first diagram, this one, it is showing us that the pressure is acting along the circumference or on the circumference and trying to increase the length of the circumference. Or in another way I can say that it is trying to, or it is inducing some tensile type of phenomena inside the material along the circumference. So if you take a small element along the circumference, the small element here, you see that it is experiencing some tensile stress, so we denote it by sigma, and the stress is along circumference, so we denote it by C here. So we call this sigma C as circumferential stress. It's also called as hoop stress. Now in the same way, if you see this diagram, we see that it is experiencing some tensile stress along the length also. So if you take this left part of this section, so it is experiencing some tensile stress along length direction. So we call this as longitudinal stress or axial stress. So these are the two stresses which are acting on this thin cylinder. So after evaluating the values of these two stresses, two normal stresses, circumferential stress and longitudinal stress, later we will evaluate the shear stress induced inside the material of the thin cylinder. First of all, let's evaluate the circumferential stress. So to evaluate the circumferential stress, let's take the upper half of the or upper hemispherical part of the thin cylinder. So if you take that, it will be like this. So here the pressure is acting in this way. So it is trying to make this upper hemispherical part of this particular thin cylinder to move in the upward direction. But it is intact by the application of or by the induction of the circumferential stress along the circumference. Now let's evaluate the value of circumferential stress based upon the dimensions d, thickness t, and also the application of the pressure here. So to see the effect, we'll take a small element like this. So this element is at an angle of theta here and having a thickness of d theta. So if you want to find out this area here, this area will be r d theta into L. So this arc length is r d theta and into the board the length is there. So the area will become r d theta into L. So the pressure is acting on this area. So force induced is equal to given by pressure into r into length into d theta. So I can show you the application of force in this diagram here. So the force is acting in this way, like this, and magnitude of force is equal to given by P R L d theta here. Now this force is having components. One is along x direction, Fx, other one is along y direction, Fy. Now if you see carefully here, the horizontal force will be cancelled by the opposite horizontal force which will be induced somewhere else in this direction. So here Fx will be cancelled out and only Fy will not be there. So sigma c will be taking care regarding Fy itself. So the magnitude of force induced corresponding to sigma c, which is in the downward direction, should be equal to the magnitude of force induced because of the pressure in the upward direction. So let me evaluate this value here. So if you take the three-dimensional view of the diagram, so in this case, vertical force is equal to given by Fy is equal to F sin theta. So sigma c is acting in downward direction and over the area here. So sigma c is acting over an area. This area is equal to given by T into L. In the same way, this area also T into L. So sigma c is acting in two places, T into L, T into L here. So that's in downward direction and Fy is in acting in upward direction. So if you take this vertical force in the upward direction, this will come as P R L d theta into sin theta. So this is a differential force here. So this must be integrated because you take it as d Fy and d F here. So integrate from 0 to pi, that is 180 degrees here. So this upward force must be equal to the force corresponding to sigma c, that is equal to 2 sigma c into T into L. So if you do the whole integration and substitute radius in terms of diameter, that's d by 2, finally you're going to get that sigma c is equal to P d by 2 into thickness. So the variation or the value of the circumferential stress is given by pressure into diameter by 2 into thickness of the material. So more is the diameter, more is the stress. So less is the thickness, more will be the stress. Okay. Now let's evaluate the value of the longitudinal stress or axial stress. So we'll take the particular section. The pressure is acting here. So if you take the three-dimensional view of this diagram, we'll get like this. So the sigma L is acting on this circumference. So only one area is there. This is the shaded area here. So although we show 2 times here, this is actually only one area here, and the pressure is acting on this area, this lower part of this area here. So the area corresponding to sigma L is equal to given by sigma L into this shaded part of the area, that is 2 pi r into T, or this can be written as sigma L into pi dt. So this force in horizontal direction is actually balanced by pressure force here, or in fact whatever the force that was created because of pressure in the negative x direction is actually cancelled out and kept this body in equilibrium by the induced stress here, the force corresponding to induced stress here. So the pressure force is equal to given by pressure P into area pi d square by 4. So if you simplify this one here, so you take the same diameter d here, so finally you will get sigma L is equal to given by P d by 4t. This is how you're going to get the value of longitudinal stress. So we see that the material of a thin cylinder is experiencing 2 normal stresses, which are both are in perpendicular direction. So if you take a thin cylinder and do the stress analysis, you will get in this way. So we see that it's experiencing a longitudinal stress in this direction, that is sigma L, and this is circumferential stress sigma C. So let's take a coordinate system here. The coordinate system is taken in this way. This is x, this is y, and this is z. So we are not having any stress components in z direction, so let's forget about z direction here. So x and y here. So we can say that our sigma x is actually taken as sigma c, so sigma L, and sigma y is taken as sigma c. Okay, so no other components are there. That means tau xy and all other stress components are equal to 0. So if you write down the stress tensor matrix, sigma x 0, 0, sigma y, this can be written as sigma L 0, 0, sigma c. Now in this case, we see that sigma c is higher than sigma L. Another thing is, we know that on the planes where shear stress is 0, we take those planes as principal planes, or they will become principal planes, and the corresponding stresses will become principal stresses. So in this case here, sigma L and sigma C both are principal stresses, because on these planes, I am shading out these planes here, on these planes here there are no shear stress components. So both become principal planes and corresponding stress become principal stresses, but whichever is of the higher magnitude, we will take that as a maximum principal stress. So in this case, maximum principal stress will be denoted by sigma 1, and that is given by sigma c, and it is given by PD by 2t. And minimum principal stress is equal to given by sigma L, and it is given by PD by 4 into t. So this is how we're going to get these values here. So if anybody asks you maximum normal stress induced inside the material of the thin cylinder, immediately you have to go with finding out sigma c, or which is the circumferential stress. I'm writing out here. maximum normal stress and this is minimum normal stress. Now you got the two principal stresses. Now to find out the maximum shear stress induced inside the material of the cylinder, we have the formula that sigma 1 minus sigma 2 by 2. So this gives you the answer as PD by 8T. This is the value here. Now here I would like to clear many misconceptions many people are actually having. Many people think that the thin cylinder is experiencing pressure in radial direction. So this pressure must create some stress in radial direction. That's actually wrong. Because we are considering this particular cylinder to be a very thin cylinder because the thickness or the material along the thickness is equal to very negligible. So we don't consider that to be a thick cylinder, but in fact we are considering it as a thin cylinder. As we are considering it to be having a negligible amount of material along the thickness or along the thickness of the material of the cylinder here, so the stress induced is neglected. So that's why in the assumptions I have written that radial stress is neglected in the thin cylinder. And even many people think that sigma r should be taken as minus p. That's actually also wrong. That's actually coming from the assumption or from the mathematical calculation of the thick cylinder there. So what they generally do is they take the radial stress component or the radial stress formula of the thick cylinder, and in that thick cylinder they put the thickness is tending to 0. So from that they will get the answer that sigma r is equal to minus p, but in fact it is actually wrong. Okay, so kindly remember that radial stress will be 0 for a thin cylinder. Okay, so when radial stress is equal to 0 for a thin cylinder, there will be no stress along z direction and we'll be having stress components only x and y directions. That means only two directions. So it's a biaxial state of stress or a plane state of stress. So simply we apply this formula that tau max is equal to sigma 1 minus sigma 2 by 2. So if you consider that like sigma r is there, then it becomes a three-dimensional state of stress. Then what are the answer you're going to get? Tau max value and all these things will be something different and which are in fact wrong. Okay, now let's see a question. It was from GATE 2008 and it was even again repeated in the bar 2016 examination. So kindly copy the question from the slide. There's a diagram also. Let me read out the question here. A cylindrical container of radius r is equal to 1 meter, wall thickness 1 millimeter is filled up with water up to a depth of 2 meters and suspended along its upper rim. Let me draw the diagram here. So it's having some water up to a height of 2 meters and radius is also 1 meter and thickness is 1 millimeter. The density of water is given by 1000 kg per meter cube and acceleration due to gravity is given as 10 meter per second square. The self weight of the cylinder is negligible and the formula for hoop stress in a thin cylinder can be used for at all points along the height of the cylindrical container. So in this question they are asking us to find out circumferential stress and axial stress, that means sigma c and sigma a at a height which is at the midpoint. So at this midpoint we have to get the values of circumferential stress and the longitudinal stress or the axial stress there. Okay, so basically we know for the formula for circumferential stress simply. So at this height we have to get the value of circumferential stress. So simply what happens is we have to get the value of pressure at this point. So at this height, the pressure is given by the formula rho GH. So where rho is equal to 10 cube, G is equal to 10 and height is equal to 1 meter. So 1 meter. So pressure is equal to given by 10 power of 4 Newton per meter square. So you got the pressure here. So at this height, we need to get the value of circumferential stress. So what is the circumferential stress induced inside the material there? So simply sigma C will become P d by 2t. So if you substitute here, P is equal to 10 power of 4 into diameter d is equal to given by 2 meters whole by 2 into thickness 10 power of minus 3 meters. So this will come as 10 megapascal. Now we are coming into the most important one. We have to get the value of axial stress here. Many people consider that here the pressure is directly 10 power of 4 Newton per meter square. So simply sigma A will be given by PD by 4T and we'll get it as 5 megapascal. This is wrong because there's a difference here. Okay, so in the earlier cases, whatever derivations we have done or whatever the what are the cases we have taken, in all the cases the cylinder was taken horizontal and we have considered that the variation of pressure is not there. Along the radius, that means here it's the height here, so there is no variation of pressure. So pressure is same, we have taken like that. Okay, so but here it's not the condition. So here the pressure is varying. So if you take at this height, the pressure is equal to 0. At this height, pressure is equal to some 2 in 10, pressure is equal to 10 power of 4 Newton per meter square. So if you go to this depth, it will come as 2 in 10 power of 4 meter square here. Understand? So let's derive the formula for the axial stress for this condition, and from that we substitute the value here. Okay. For this case, if you take down the bottom part of the section, here we are experiencing sigma A, and the sigma A is actually balancing the pressure induced in the bottom surface. Okay, so pressure can act only on the surface here like this. So whatever the force that is induced because of pressure in the horizontal direction, that will not be cancelled by the force corresponding to axial stress. So only the vertical pressure force will be cancelled out here. So at this location, pressure is equal to given by, at that location pressure is equal to given by, pressure at bottom is equal to given by rho g h. So where h is actually 2 meters. So this will come as 10 power of 4 into 2. So 2 into 10 power of 4 Newton per meter square. So this is actually cancelled by sigma A here. So anyhow, if you write down the formula, we will get sigma A into pi dt is equal to given by pressure into pi d square by 4. Wholly you will get sigma A is equal to given by P d by 4t. But here the pressure is equal to given by this bottommost pressure. This pressure we have to take it here. So simply sigma A will come as 2 into 10 power of 4 into diameter is 2 by 4 into thickness is 10 power of minus 3. Again this also comes as 10 megapascal. So this is only one question which is little bit different from all the other type of previous gate questions from this particular chapter. And trust me, this question's answer was wrong in many of the question banks. So this is actually the correct answer. That's why this question was repeated in bar 2016, and those people who has given the answer as 10 megapascal for circumferential stress and 5 megapascal for axial stress, they got negative marking. Those people who has given answer like this, 10 megapascal, those people only got the correct answer and got the positive marks. Understood? So this is how you're going to solve the numericals from the topic of thin cylinder. So you can go directly and open up the chapter of thin cylinder and you can solve all the previous gate questions very easily, which are corresponding to finding out stresses. Okay? Thank you so much.